Yeah. So you mentioned that like there's like AIs now that can it'll just like give it like basic high level abstract instructions. I got like access like GitHub Copilot like a couple like months ago. It was like it's actually been like so nice. Like earlier like code that like used to take me like 10 minutes to write would just like take me like one line of saying go just like do this and then it generates everything for me. And also like the aspect of like interpretability and explainability also is like really important as you mentioned. Like I think like explainable AI is like a really big topic now, and having like the especially with like language models because like as you mentioned like this black box effect, it kind of makes it like hard to I guess like understand like what's going on behind the hood. There's like so many services right like nowadays that are built on language models that like, you kind of just like you put stuff in and you don't exactly know what's going on when you get the output. So having like that kind of iterative process also sounds like it'd be very promising.
Yeah, I mean, it's a very actively researched area right now because people all want to know why the language model produced what it did. And it's a very hard problem because these things are immensely complex systems, and they're completely black boxes. And to some degree, I think it's remarkable what we're seeing with AI, right? I mean, a few years ago, I think it would have been hard to say for sure that if you gave these systems lots of data about human interactions or human conversations or whatever text, that somehow they would learn more general notions and be able to produce novel code or whatever, right? And so I think that's remarkable, and I think it speaks a lot to how much is encoded in human communication, implicitly encoded in human communication. And those patterns are what these models pick up. And I think that in and of itself is quite a remarkable finding for us, for humanity as a whole.
Absolutely. I also think it's fascinating how much artificial intelligence has truly grown over the last 2 years through LLMs and NLP as well. I've found that most of your research, as you mentioned yourself, is always focused on the humanities aspect, specifically regarding cognitive science or behavior. I was wondering if you could elaborate for our listeners what escape means in one of your research papers and the implications from that research paper.
Is this one of the new ones, the recent ones that you were looking at?
I believe so, yeah, 2024 paper.
Yeah, so I believe that this is the same paper. I mean, Escape was a paper that we wrote that I actually did a lot of work on several years ago with a couple of colleagues. And the whole idea there was that that whole idea there was to understand how humans do creative problem solving. And in creative problem solving, one of the challenges is that you're given a problem and that your model of the problem is somehow not enough to solve it. So you get stuck. You're not sure where to go with it. But somehow humans are able to get out of that, get unstuck, and find new ways of dealing with that problem. The question is, how do we do that? And what's super fascinating is that there has been over a century of research in the psychology space in a related area called insight problem solving. And insight is when you get the aha moment, right? You're doing something and all of a sudden there's a flash of genius and you're like, oh my God, that's how I solved this. Maybe you don't even get it while you're solving the problem. Maybe you get it while you're in the shower or you're taking a walk. Maybe you get it when you observe something completely unrelated, but your mind has drawn the analogy that that's related to the problem you're at hand and you solve it. So psychologists have studied this for a really long time, and there's some really cool theories around this. People have developed all kinds of very cool toy problems. I think one of the most famous ones is the 9-dot problem, where you're given a grid of 3 by 3 dots and you're asked to connect it with 4 lines. And it's really hard. It's really hard to do that if, I would encourage the listeners to go and think about that and draw a 3 by 3 grid and try to connect it with 4 lines. Your mind makes so many assumptions about what you can do there, but it's very hard to get out of those assumptions. And like that, there's many other toy problems that psychologists have worked on for a really long time. But what's been missing throughout the entire 100 years of this literature is an investigation into the actual cognitive processes that are taking place when people solve these problems. And part of the reason for that is because it's really hard to inspect and look inside your brain while you're solving it. So back in the day, people would do what's called verbal protocols, which is as they were solving, as the participants of that experiment were solving the problem, they would speak out loud their solution process. And those are then tracked and kept, and then people would study them and see, okay, here's how they might have solved it. But often those can be either incorrect or not an accurate representation of how the human actually solved it, and they can be distracting for the person themselves, and so affecting the whole data collection process. So there were some issues with that. More recently, there's been some great work by Professor Mark Beeman out of Northwestern in the neuroscience space, where they use a similar kind of small set of insight problems. It's called the compound remote associates task, which is basically they give you 3 words and they say, what is the word that links these 3 words together? And often that's also considered to be an insight problem. And what they do is they've now been looking at EEG signals, fMRI type data, and they're trying to observe what's happening in your brain as you solve these problems, and what kind of waves are activated, and what kinds of systems in your brain are activated when you get the aha moment and when you do solve the problem. And so that's been very fascinating. But again, what's missing in all of this is still sort of algorithmically, how do we go about solving them? Like, what is, if we were to build a computing system that does that, it's not clear exactly how we should do that, and so I think that's kind of where that project started. And the idea that I had there was potentially using puzzle video games. So puzzle video games, and I don't know, I'm not a huge video game player, but I do like puzzles. And so puzzle video games are a class of video games that you deal with these kinds of issues where you have to get past a certain obstacle. And the way to do that is kind of non-intuitive. You might have to do something that actually makes it harder before you realize that actually makes it easier. So, and games like Braid and Portal, and there's a whole bunch of others that are like that, where you have to do something completely non-intuitive that seems like it's the wrong answer, but that's the way to get solving the problem. And so I thought that might be a really nice framework for exploring this, because the video game framework allows a more, you can measure people's eye, you can eye track, you can watch them play the game, you can see where they click on the screen, you can track a lot more variables beyond what people were doing in the past. And so that was really beneficial with that. And so the particular paper that we worked on was, we created a game that we called Escape Room. And it's essentially like you would imagine an escape room setup is, where you're locked in a room and you're trying to get out. But humans, when we see objects, we attach meaning to them. So if you saw a key, you know immediately that a key is a key and it can open doors and such. So we wanted to take that out, because AI systems don't know that right up front. They might be completely empty and they don't know what any of these words mean. So we created this kind of grid world kind of game, which has everything is abstracted out. So just what seems like a room, like it's like a gray box, and there's a goal, like a green square that you have to get to, and you're a white square, and there's some other colored squares in the middle, and you can move up, down, left, right, and that's it. And so we watched, and then what we did was we watched humans move that white block around till they get to the green square. And we created these puzzles to be increasingly more and more complex, as there was like 12 or 13 levels, and each level got more complex. And the way they got complex was either by adding more different things that can be used, or by making the game more complicated. Like they had to make new discoveries. So all of a sudden there was a new pink block that they didn't know what it meant. So they had to play around with it a little bit, figure out what it can be used for, and then use it to solve the problem. And so, these blocks had meaning, but they didn't know that. These blocks, to me, this was a key block, and this was a door block, and so on, just so that I can construct these puzzles. But people participating in these experiments don't know that. And so we thought that would be a really nice paradigm, a paradigm that can potentially be used in an fMRI EEG study as well, because you're just clicking buttons. So potentially you can do these kinds of experiments in many different settings. And the nice part is there's a direct computational correlate with this. The whole world of reinforcement learning uses grid world type puzzles to explore different algorithms for learning them. The world of AI planning does the same thing. So we thought, okay, maybe this is a nice way to understand human cognition by tying it directly to this kind of discrete grid world in this way through puzzle video games.
Oh yeah, it's really cool. Actually, on the subject of puzzle games, my favorite game right now, I'd say, is Tetris. I've played hundreds of hours the last couple of months. But and talking about the aspect of cognition behind that, I know like reinforcement learning also like when it comes to bots that have been made to play Tetris, they've talked about like using like Q learning algorithms and reinforcement learning in that sense. And I think it's like really cool how you guys like kind of tied that into like a methodology for gathering more insight on like how humans process things. I think like video games is like a really like fun paradigm of doing that too. Like out of curiosity, could you like or like kind of like what was your methodology with like actually testing how Escape worked?
Yeah, I mean, the specific experimental protocol was we would show people the game and have them play it. And we saw how far they got. I mean, I think we gave them a 5 minute, actually, they all got through all the 13 puzzles, but we showed them, we gave them 5 minutes for each puzzle. And the first puzzle was really straightforward. So like you can just, it was like a gray box, which one would assume would be a room. And there was a little opening and there was a green box outside of the opening, a green square outside of the opening. And you were the white square and you would move, you could just move right across and get through the green square. That was the first level. It was super easy. But then the next level, the opening was closed with a blue square. And so you didn't know what the blue square was, so you would still try to go through, but obviously you couldn't. So then people would start to explore the space and try to figure out if there was some other way to get across. And so we just made them do all the different levels. And then when they were done with that, they then were given a questionnaire in which we asked them their thoughts about what they did, sort of after the fact. We also gave them new positions and asked them to explore those and see if, we were trying to understand also if people thought certain problems were impossible. And we knew for a fact, because some problems, we can design them to be completely impossible. And some problems can just be difficult, but not impossible. So we were wondering if humans could tell that difference. Because in the real world, you don't know, right? A new problem comes up, you don't know if it's unsolvable or not. And so we wanted to see if humans could come up with some of that. And so I think that kind of, so we did this experiment using all of this. And there were some very interesting insights gained from this experiment too, because it gave us a sense for how humans sort of think about this space. We try to attach stories to everything. So there were many humans who try to, attach meaning to these blocks before they would try to solve them as a heuristic for being able to solve them quickly. And unlike reinforcement learning algorithms, humans learned very, very quickly. Like just a few clicks here and there, and we were able to figure out what the block did and use it right away, which is something that, and we didn't do, humans didn't do kind of random actions, right? So you see a lot of reinforcement learning algorithms, the exploration phase involves just moving around, right? And so, but the humans didn't do that in a meaningless way. It was very targeted. It was very much, I want to try this thing. Okay, that didn't work. I'll try this thing. So it was very targeted. So I think there was some interesting findings on that front too, as well. And I think that we're sort of only scratching the surface here. This was just a first preliminary study, and I think there's some really cool work to be done moving forward.
Mm-hmm. And like on the topic of like, sorry, go ahead.
Yeah, so I was just about to say, on the topic of like the research aspect, I think it's really cool that you mentioned how that like in the past they used to do this with human examples with verbal feedback, and how that methodology might have affected data collection itself. But now with these newer mechanisms, we're able to track not only more variables, but the study itself has less loopholes and less variables that can't be tracked, allowing for a more validated study within the field. And like you mentioned, we're only scratching the surface with this research, so it's very impressive to see forward what we'll be able to accomplish. Arman, you want to add something?
Yeah, sure. So I was just gonna like ask, I guess like, what kind of work should we expect from you in the future? So like, what are you working on right now? What do you expect to be?
Yeah, like I said, my big focus right now is on human reasoning. I think that to me is fascinating, and it could that's both social and creative reasoning. I think there's so many interesting issues that I would like to work on, and I am working on, and that all gets at the different facets of human reasoning. And it's not just about solving math problems and reasoning with that. That's one type of reasoning, but there's all kinds of other things. So there is flexibility in our problem and representation. So the example for this would be, say you were driving to the airport and your car's parked in your garage. You might make a plan. You might say, okay, I'm going to take, I-95, and I'm going to do this, and I'm going to make my plan. You make this high-level plan, and you're excited. You get into your car, you load your bags, and you jump in, and you start the car, and the car doesn't start. So now, for at that moment, you don't care about the overall plan of whether you're going to terminal E or D or whatever. You care more about that specific issue about the car starting or not. And what I find fascinating is at that moment, you immediately only care about that world. And until that point, you didn't care about whether whether you had enough, gas, or whether your car has some electrical issues or whatever. But now you do. And that all of that comes in and your brain is able to take in all the relevant information and start working on that problem immediately. That is something that is absolutely amazing to me as well. That's a flexibility in our thinking and our problem representation. So I think that's one aspect of reasoning that is super fascinating. Another aspect is what's popularly called theory of mind, which is a type of reasoning that we do that is reasoning about other people's thinking. And to me, this has always been super fascinating to me, and there's been more work on this recently. The large language models have some ability to do that, but they're not that great at more complex tasks that we humans do. And again, for this, I have a great example, which is, there's an example where there's these two characters, there's Pete and his mother. And Pete's mother buys him a bike for his birthday and puts it in the basement. But then when Pete asks about that, or doesn't know about that, but asks about whether he's getting a birthday present or a bike or whatever, his mother lies to him and says, no, you're not. So at this point, the question is, what does Pete's mother think that Pete believes? And Pete's mother thinks that Pete believes there is no present because that she just lied to him. But then at some point during the day, Pete goes down to the basement and sees it and then comes back up. And then now the question is, what does Pete believe that his mother believes? And again, Pete knows that it's a bike that's for him, but he still believes that his mother has the wrong belief about this, about his own belief. So you can start to see the nesting here that happens with this. And we're able to immediately reason about, you guys are able to immediately reason about this. And then there's another variant of this, which is, what if Pete's mom peeked in while he was in the basement? So she saw him looking at the bike, but he didn't see her. So now all of a sudden, Pete's mom has the correct belief about Pete's knowledge of the bike, but Pete doesn't about his mom. So I think that this is a very exciting area of research, which, as it turns out, is really critical in all kinds of applications. Any kind of human interaction application, you're going to have to be able to reason about other people's beliefs. So that's something I've been sort of working on a little bit. There's this whole area of, like I said, argumentation that kind of overarches all of this. And I've got a couple of projects that I've been kind of working on as well in having AI systems help humans do better critical thinking, combating misinformation, all of these things. If there's a certain amount of critical thinking that happens, there's a chance that maybe we won't get easily swayed by a lot of the misinformation. And so, AI systems can potentially do that, can build arguments and help you build better arguments as well. So that's some of the research that I've been sort of focused on and going forward. The creative problem solving piece is always there as well. The creative reasoning piece is huge. And, overall, I'm interested in how can these AI systems be better team players? How can they be better teammates, better coworkers, better collaborators, better communicators?
Yeah, that's awesome. We and our listeners are looking forward to reading your work in the upcoming years. So keep up the good work.
Thank you.
And it's a final question. We talked about the cartoons earlier. We were just wondering if you had a favorite. Personally, I felt the student government one with the fish was pretty cool.
Thank you for looking through my cartoons. Those I made them during my lawyer years, and it was very easy to make fun of lawyers. So I was able to make a lot of cartoons very quickly. I don't know, my favorite one, there was one that I did about patent law in which there's a lawyer in a courtroom, and he's talking to a judge, and he has a blackboard next to him, and the blackboard has all these complex mathematical equations. And he says, and the caption reads, "See, Your Honor, it's obvious." Now, what I like about this is it's kind of niche, so not everybody understands it, and it's niche to the patent world, because I was a patent lawyer then. And the notion of obviousness is a very core patent concept. And anytime you get a patent, the invention has to be novel, useful, and non-obvious. It means that somebody with similar skills shouldn't have just thought of that. It required some kind of mental leap in logic or whatever. So it's not obvious, not an obvious extension of what's already out there. But I thought it was really funny because, this is here, there's this lawyer speaking to the judge with all this complexity, which the judge may not be understanding, and talking about how it's obvious. So that's one of my one of my own favorites of my own work. As far as the general space of New Yorker cartoons, there's so many that I love. There's one that I love that has two people sitting in an airline seat, and one person is on a computer. Clearly, like you see all these people working, business folks working on a computer in an airplane. And so this other person is sitting next to them and leaning over and pointing at something on their screen. So kind of being rude, right? In a sense, pointing over and leaning and reading. And the caption reads, "You spelled confidential wrong." So I think that is one of my single favorite cartoons. Yeah.
Yeah, absolutely. I know that Armand and I are going to start looking through your work and the New Yorker's work a lot more often nowadays. Thank you for listening to the Neural Network. It has been a pleasure to hear how Dr. Sarathy is working on making AI a team player for all of us. That's Vasu, Armand, and Dr. Sarathy signing out.